Okay, so here we go. So last time we talked about, we were using my 219 notes instead, but we talked about all this stuff here. This was the very beginning of the section on curvature and acceleration. We are actually skipping that section, most of it. It used to be part of the course. It got removed for a combination of reasons. I leave these pages in the notes because it's still pretty cool stuff, and if you want to take a look, I encourage that. It's really nice practice with, for example, making clever uses of cross product and dot product, and with some really nice geometry in this picture, for example. So if you want to take a look, you're welcome to, but it's not part of the course. You're not responsible for it. It's not fair game for any of the exams. There's not going to be any homework stuff on it. But that said, this very first little bit where we talk about the dx vector, in particular, what the dx vector is and how to think about it, and then you may recall I also introduced the capital T, the unit tangent vector, also is part of the course. Okay. So, all that said, moving on now, we're going to skip all this stuff about curvature and dive into the section on surfaces in R3. So here we go. Typically if you have an equation of three variables, and when I say an equation of three variables, I mean something like this. And you may object and say, does it have to be a zero on the right? It doesn't have to be a zero on the right, but whatever you have on the right, you could whip it over to the left-hand side by subtraction, and you can always put it into a form that looks like this. So just for convenience, it's kind of nice to think of it as where there's a single function involved in defining the equation. Okay, so typically if you have two variables, that gives you a curve. If you think about it, two variables, one equation, and 2 minus 1, it gives you then a one-dimensional curve. That little subtraction works here as well. If you have an equation of three variables, one equation, you subtract, you get you would think a two-dimensional thing. That is, of course, a surface. Okay, so anyway, that's just a sort of a point of view. What we want to do now is try to understand, given an equation, how do I figure out what the corresponding surface looks like? There are some techniques for this. They are not perfect. In the sense that I'm not going to be able to show you how to find and understand every single possible equation of three variables. But if you think about it, we didn't do that in two dimensions either, right? I mean, I can write down all sorts of equations of two variables that we don't know how to even get our hands on, right? There's certain tricks that work in certain cases. So that's going to be the case here as well. Okay, so first tool. Again, tools for your toolbox. That's what we're doing here. We're going to talk about something called a cross-section of a surface. And a cross-section, the big idea is this is taking an intersection with a plane. And the reason the intersection with a plane is because planes are typically really easy to write down equations of, especially if you're talking about planes parallel to a coordinate plane. They're really easy to write down. Right, so here we go. Here's the big idea. We have this surface that we're trying to understand. I don't know what that thing looks like by itself. But if I talk about the cross-section at height 4, for example, what does it look like if I take a cross-section of this by the plane z equals 4? Well, I'm going to set z equal to 4, but then don't forget I'm looking for the intersection with this that I already have up here. And an intersection means that I need points that are on both surfaces, which means I need points that satisfy both equations. And if I know that z is equal to x squared plus y squared, and furthermore, I also know on this intersection I'm interested in that z is equal to c, well, together that means that x squared plus y squared has to equal to c. And notice this is an equation of now only two variables, right? So this strategy, this cross-section strategy, is a way of turning an equation of 3 variables, where I don't really know how to deal with it, into an equation of, well, now only 2 variables, where I have more techniques, more experience, more locked and loaded standard. I know what that is already. I don't even need to think about that. That's a circle, right? So that intersection is a circle. And you could repeat this process for various different constants. I mean, over here I did it for c equals 4, but you could set z equal to 1 instead of 4, or all the algebra is morally equivalent, and so that gives you a different cross-section like that. That makes sense to everybody? Okay. So that's the big idea. It's called a cross-section. Some people call this a trace. I like the word cross-section. I think it's more relatable, sort of real world. Anyway, now, does this knowledge here perfectly identify our surface? Not really. I see the cross-section. The horizontal cross-sections are all circles. I mean, here's the thing. There's lots of surfaces where the horizontal cross-sections are all circles. I mean, it could be a cone, as far as I'm aware so far. It could be a bowl kind of a deal. It could be, I don't know, maybe it does like this, right? The mere fact of having circular cross-sections does not fully answer the question for us. So what I'm going to do then is talk about a different cross-section. Now this one's going to be geometrically challenging, right? This is hard to draw, hard to visualize. I'm going to now look at cross-sections perpendicular to the y-axis. Now, perpendicular to the y-axis gives me planes that look kind of like this. Right? Those are all perpendicular to the y-axis. Now, what happens when I plug in y equals c, as you see it like I've done here? And notice what that gives me then for my cross-sections. Bunch of equations that look like this. Now, what on earth am I going to do with that thing? I've got x squared plus c squared equals z. Well, do notice now that is an equation, 2 variables. In fact, that's a highly recognizable equation because z, which you might think of as the output if you prefer, right? But it's x squared. Oh, and then plus some constant called c squared. So z equals x squared is a parabola. That's easy. So this is a parabola then. It's a parabola that's shifted upward, you might say. Right? And it's shifted upward by the square of whatever your y coordinate is. Basically, is how to think about that. So I then draw for this thing. You can see when we choose c equals 0, then c squared is 0, which means that here I'm shifting upward by 0, and I get a parabola in that sort of middle cross-section, if you will. Okay, now let's look at what happens if I have here where c equals 1. If c is 1, then 1 squared, of course, is 1, which means I'm shifting upward. Let me do this in a different color now that I think about it. I'm going to be shifting upward by 1, which means now I still have a parabola. It still equals x squared, z equals x squared plus something. That plus something is now 1 instead of 0, but it's still a parabola, and so it looks a lot like the previous parabola. It's just that when I move over to the right, because of picking a different cross-section, I also move up because of what the value of y does in that cross-section. Everybody with me? And then likewise, what if I look over here where y is equal to -1? Well, if y is -1, then c is -1, which makes this again +1, shifting upward again by +1 because that c is squared, right? And so again, I get this sort of shifted upward parabola. So now, does this give me a complete picture of my surface? I don't know. Maybe if you're much better than I am at visualizing things three-dimensionally, this is also kind of hard to work with. And by the way, also artistically challenging. Right? It's very tricky to draw this. And let me drop a suggestion here. I'm going to be dropping the following suggestion multiple times throughout this course. This course is unavoidably and intrinsically geometric. That's what it is. You can't get, there's no way to work around this, right? So if you're trying to visualize things three-dimensionally, there's no getting around the fact that being able to draw three-dimensionally reasonably well is unavoidably helpful. It's almost essential. Now, I'm well aware of the fact that many, possibly most of y'all might not consider yourself to be good at drawing three-dimensionally, right? It is hard. It takes a lot of sort of insights and got to know the tricks. So I throughout the years have some what I consider kind of hard-won lessons from all my experience of trying to draw these kinds of things and struggling and realizing what the problem was and learning from my mistakes, etc. And so I've put all of my hard-won lessons of how to draw well three-dimensionally into a couple of videos. They're on the YouTube channel, same YouTube channel where our recordings are going. Different playlist. So what you want to do is go to my YouTube channel, find the playlist called Miscellaneous Topics. In that Miscellaneous Topics playlist, there's actually several recordings, but two of them in particular, Drawing 1 and Drawing 2. And Drawing 1 is basically some general methods, general sort of tips and tricks. Drawing 2 is some in-detail examples, starting from the relatively easy and moving up to the pretty darn challenging. So I think it's, if you consider yourself, like I think probably most of you might, not that good at drawing three-dimensionally, I think you'll find those videos really helpful. I hope you'll give them a look. One way or the other, and you can see from this example, it's going to be really useful to be able to draw three-dimensionally. So however you prefer, it'll be important to make sure you've got chops on that. Okay. All right. So now what have we got all together here? We've got, let's see, I'll zoom out so we can see better. I know that the horizontal cross-sections look like this, and the Y, perpendicular to the Y-axis, vertical cross-sections look like this. Between the two of them, I kind of feel like I can sort of piece it together, and I feel like this is a bowl. Right? I mean, it's, hard to kind of do all that geometry, but I feel like it's something kind of like that. Does that seem believable? Okay. All right. So, now, at this point, the next few tricks I'm going to show you, I have better copies of in my other lecture notes here. So I'm going to switch over to the Math219 lecture notes. By the way, quick reminder, all of these Math219 lecture notes are in the course materials folder on the class website. And we're in the chapter 2 notes here, by the way. Oh, and you can see where I am in the notes by looking way down here in the bottom left corner. I don't know if that's legible, but it says right here, it says page 8 in the little readout at the bottom left. And furthermore, if at any point, if you can't read that and you'd like to know where to get this exact page of notes, just raise your hand, let me know, hey, what page are we on, and I can read it and just tell you what page we're on. Okay. All right. So, here's the big idea. Next tool. Next tool for your toolbox. Sometimes, not always, not even necessarily all that often, but sometimes an equation that has x's and y's in it, those x's and y's will appear only as part of this expression, square root of x squared plus y squared. And actually, you'd be surprised how often that comes up. It's kind of arbitrary seeming. What you will notice, though, is that is the distance from the z-axis. Kind of a quick observation there. Right? So if you have an equation where there's x's and y's, but they appear only, and I emphasize only, as part of this expression right here, then there's this wonderfully powerful conclusion that we get basically immediately, and that is our surface is rotationally symmetric around the z-axis. It's awesome. Right? If you know that your surface is rotationally symmetric around the z-axis, that is a tremendous amount of information. And you get that tremendous amount of information at a glance. Just look for where the x's and y's are and make sure that they're all stuck inside of an expression like this. That's it. That's all you got to do. Eyeball glance, powerful geometric conclusion. This is an awesome tool for doing three-dimensional sort of algebra and surfaces and that sort of thing. Okay, now why does this work? Well, why does this work? Let's consider a couple of points, like this one here to start, and then imagine that I rotate it around. Hypothetically, imagine that I rotate it to produce this point here. Well, no, those are different points. Totally different points, right? They're not the same point. A different point, among other things. They have different values of x and y. Well, of course they do. They're different points. But notice, they have the same value of what I'm calling r in the picture there. The same value of square root of x squared plus y squared. Because I rotated around the z-axis, and distance from the z-axis doesn't change when you do that. They also, notice, have the same value of z. Because you rotated around the z-axis and that doesn't change the height. Right, so now if you think back to the equation, what was the deal with the equation? The equation involves x, y, and z, but not really fully independently. The equation really only involves x and y in only that form, and then z. So as far as the equation's concerned, these 2 points have the same values of everything that actually goes into the equation. And so either they both work, or they neither work. And so the conclusion then is, well, that means that this surface is rotationally symmetric. Does that make sense to everybody? It's a wonderful little, convenient little argument. Oh, yeah?
What do you mean by they both work?
Well, yeah, so when you plug a point into an equation, either the equation is true, and by which I mean the equation worked, because when I plugged it in, I got the same thing on both sides. Or the equation might not be true. Yeah, right. Okay, so that's the big idea. Now, what we're going to do with rotational symmetry, and real quick, if you know about cylindrical coordinates, here's an alternative point of view. There aren't any thetas in the equation, in the cylindrical equation, and that can also argue rotational symmetry. If you don't know cylindrical coordinates, I don't want to go down that road just yet. We'll introduce cylindrical coordinates a little bit later in the way Math212 is set up. But anyway, if you happen to know it, for your consideration. Okay, so the reason we care about this, when you have a surface with rotational symmetry, you can look at its cross-section in any plane that contains the axis of rotation, in this case the z-axis. Just look at its cross-section, and then, well, you can just rotate that cross-section. It's rotationally symmetric. All the cross-sections look exactly the same. So pick one, doesn't even matter which one, and then rotating that around will generate your entire surface. And this is something that we can actually actionably do. And let me just show you an example. You'll see this happening. Now here's that same surface we were looking at on the other page, right? We had to draw some nasty pictures and challenge our artistic capabilities and then try to visualize, try to assemble these pictures together in our mind. Very challenging. Okay, check this out as an alternative. There are x's and y's in my equation, but I claim they appear only in the special form. And to the objections of, hey, where's the square root? No problem. Notice I can rewrite the equation like this. And as required, x and y appear only in that special form. All right, so keep that in mind. I mean, you're allowed to write things in different ways, and that's fine. Okay. So, x and y appear only in the special form. I immediately know that this is rotationally symmetric around the z-axis. I immediately know that I can pick its cross-section in any plane containing the z-axis. Take your pick. Right? And that'll be enough to answer the whole question for me. So here's what I'm going to do. I'm going to look at its cross-section in this plane right here. That's the plane x equals 0. By the way, watch out for this confusing little landmine. It's the YZ plane, but it's x that's equal to 0. That's confusing, right? People get that backwards and accidentally, inadvertently write down y equals 0 because they're thinking YZ plane. Anyway, I'm sorry, that's a little landmine of geometry there. But in this plane, it's really easy to understand what this surface looks like. Really easy. Because, after all, if x is equal to 0, plug that right in there, right? This equation then just becomes z equals y squared. That's easy. That's a parabola. So inside of this YZ plane, I know the cross-section is a parabola. And I also know that because of the rotational symmetry, I can just take that and, let's see how I can draw this. Rotate it around the z-axis. And notice that assembles a bowl, and it's much easier to see that this is a bowl because you're literally looking at a cross section of it, and we know it makes it a round thing because it gets rotated. Everybody happy with that? I think this is a wonderful technique. I think this is dramatically underemphasized in our textbook and many others. I think it's an awesome point. Okay, now just a little bit of semantics, and there's going to be a certain amount of this. This is called a paraboloid. That's just terminology, but anyway, that's what it's called. Let's see another example. How would I understand this surface? Right. Hard to tell at a glance, right? We don't really recognize this exactly, but notice x and y appear only in the special form, rotationally symmetric. We're going to be able to make a rotation argument. We're already encouraged. Everybody with me? Okay. All right. So now pick your favorite plane. Now just to mix it up, here I'm going to pick the xz plane. Doesn't matter. I could pick the YZ plane if we wanted to. It's fine. Any cross-section works. But again, just for mixing it up purposes, pick this plane. This is where y equals 0, which is easily plugged into there. The cross-section then is this. X squared minus z squared equals 1. Easy algebra. Just plugging in y equals 0. Nothing to it. Now the hard part, you do have to remember back to high school algebra 2 or whatever they call it these days where you studied hyperbolas, and I don't know about you, I always found it hard to remember, wait a minute, which way does the hyperbola go, right? It's really confusing. Do whatever you got to do to make sure you're good on this, right? But come to office hours if you want to know my little personal hack for how I remember it. But make sure that you're good with all your high school algebra, and this is this hyperbola right here. So again, rotationally symmetric. I know what one of the cross sections looks like, and so by rotation then this generates something that looks kind of like this, and I don't know what to relate that to in the real world, but it's something like that. And the name for this, by the way, this is called a hyperboloid of one sheet, just for establishing the semantics. Everybody see the process there? Okay. All right. Now, let's see here. I think we're going to do one more. There's a similar argument that you can make if you want to talk about rotations and symmetries around other axes. Right now, why have we been rotating around the z-axis here? It's pretty arbitrary. But it's because it's the z-axis that the relevant distance involves this expression involving x and y, And that's kind of the sort of what makes it work. So by analogy, now I think it's a good idea for y'all to think through the reasoning in full detail on your own, right? It's a good exercise, a little mathematical weightlifting. But the same argument works, for example, around the x-axis. And now you look at this equation and it doesn't seem to quite work, but notice you can rewrite it like this, and in this form, y and z appear only in the special form, and thus this is symmetric around the x-axis. Believable? Okay. So, all right. Now, you do have to be a little careful with this. I mean, one of the rules is whatever your axis of symmetry is, the plane that you pick has to contain that axis, right? Remember, that is one of the important details. So I, for example, am going to pick this plane. I could have instead picked this plane like that, pick the xz plane. But what you cannot do, you cannot pick the YZ plane here. It does not contain the axis, right? You have to pick a plane that contains the axis of symmetry. So anyway, proceeding, here we go. Again, this is the XY plane. It contains the axis, and it has an easy equation, z equals 0. So we're going to do the same deal we've done before. We're going to plug that into there. We're going to interpret our equation cross-section in that blue z equals 0 plane. And again, hyperbola. Right? And again, you got to think it through. Which way does it go? Oh, gosh. And this one goes like this. Rotate around the axis of symmetry. Rotate that around the x-axis. And all together, then, you get, oh, this is really hard to draw. I like to think of this as, to me, these look like contact lenses. And the contact lenses are kind of like pointing toward each other. I don't know. That's the best I got. But anyway, this surface here, it's also a rotation of a hyperbola, so they like to call it a hyperboloid, but we have to distinguish it from the hyperboloid we just saw. This, you'll notice, has kind of two separate chunks in it, so they call this a hyperboloid of two sheets to distinguish it from this hyperboloid of one sheet. Okay. Is everybody happy? Moving along. So, sometimes the equation we're interested in isn't something particularly familiar. It's not something that we can just sort of, play a rotation argument with, or maybe recognize, or something convenient. But sometimes it's a tweak of an equation that we do understand. Yeah, question.
I'm sorry to backtrack, but how can you tell if it's two sheets versus one?
Yeah, you have to think through the reasoning. Yeah, it's very hard to other than memorizing a list, which I don't recommend because you will forget. It's a question of time. You really have to think through the argument here, right? So, I mean, if you were to present me, off the cuff, without me planning it in advance and say, hey, what does this look like? I would have to sit down and go through this reasoning and think it through before I realized what it actually looked like. Yeah, sadly. Now, again, it is possible to memorize, but again, two things that are wrong with memorizing the complete list. First of all, there's like 32 of them, depending on the various forms this could take. Too much to memorize. Second of all, memorization is not reasoning, right? And so you got to keep in mind, if on an exam, if I give you this equation and ask you, what surface is this? I'm not interested in the answer. I'm interested in the reasoning, right? And so what I'm looking for in a question like this is the reasoning that gets you there. So, you really, combination of reasons, you really have to go through the arguments. Is everybody comfortable with that? Does that make sense? Okay. All right. Okay, so yeah, sometimes you want to tweak an equation, and so for example, here's one that I understand. I already understand this equation right here because it's got just tons of rotational symmetries for one thing, right? X and Y appear only in the special form, but furthermore, Y and Z appear only in the special form. Oh, and check this out: X and Z up here only in the special form. So we've got rotational symmetries galore. And take your pick, make the resulting argument, and what you find is that this thing is a sphere. Easy argument. Okay. So that I understand. Now, question, what is this equation? Okay, in this case, yeah, I could make a rotation argument. But let's pretend we didn't want to make a rotation argument. Consider a more general case where there is no rotational argument to be made, right? That could certainly happen. How would I take my understanding that I already have here and translate that to helping me understand the new equation? Yeah.
Maybe understand that in order to have the equation be correct, you need the values of z to be half.
Yeah. It was a rhetorical question. Yeah. No, yeah, totally. You're exactly right on. But yeah, let me walk through it slowly and carefully. Yeah, no worries. Sorry, I ask a lot of rhetorical questions. Okay, so rhetorically, what am I going to do to figure out how to use the green information to draw conclusions about the blue question? So what you're going to notice, the process that I've done here, the thing that relates the green and the blue equations is that from the green, everywhere I saw a z, I replaced it with 2z. Right? So that's just algebraically, that's the little copy, paste, find and replace, that I did. Every z got turned into 2z. So, alright, now let's try to figure out what does that action of replacing z with 2z, what does that do to points that work in one, do they work in the other, etc. You can kind of think through some points. Here's one, this point right here, 3, 4, 12, that works in this equation, very obviously fails in that equation. Perfectly obvious, the arithmetic just doesn't work. Why doesn't the arithmetic work? Well, it's because, just to be blunt, this 12 was supposed to be the thing that got squared. Over here, 12 was the thing that got squared. But over here on the right, it gets multiplied by 2 and becomes 24 before it gets squared. And that, again, is the wrench in the works. It just messes everything up. So, seeing that that's what's gone wrong in the arithmetic, makes it clear how to sort of fix it. The workaround then is to realize that 6 in place of that z coordinate. Plugging in that 6 there, when you multiply it by 2, gives you the 12 that you wanted to get squared in the first place, and everything works. So, the punchline then is, let's see here, just getting rid of the sort of all this stuff. Whatever you do, I'm going to need to rewind. Here we go. Whatever you do to the variable in the equation, here I replace z with 2z. Kinda, sorta, in some sense, the opposite happens on the surface. Notice that the 12 kinda had to turn into a 6. I divided the z coordinates of solution points by 2. So in this case, I'm going to call that a kind of a squishing. All the z coordinates get cut in half to make points that will actually work. So this is the sort of the big idea here. Whatever you do in the replacement, however you tweak the equation, solutions have these sort of the opposite happen to them. Okay. So does everybody believe this? Everybody kind of see how the arithmetic makes that seem plausible? So here's an example, and this is a wonderfully convenient example. Somebody comes to me with this thing right here and says, how do I understand this equation? And the very first thing I think is, I'm dead in the water. X and Y and Z. None of the pairs of variables appear only in the special form. There's no rotational symmetries here. There's not. Okay, so I guess I could start playing cross-section games, but that's artistically hard, and, not that I couldn't do it here, but the much more satisfying solution is to say, look, I know what this looks like. That's a sphere. That's easy. Recognizable even, right? And then just notice that everywhere there had been an X, it becomes X over A, meaning that there is, let's think this through. X got replaced with X divided by A, so the X coordinates are all going to be stretched. The X coordinates are all going to be multiplied by A. Again, there's that oppositeness to make it all work, to make it fit. Right? So this green surface that I'm trying to understand is the result of starting with a unit sphere and then stretching it by a factor of A in the X direction, and then likewise, because of what happens to Y here, we're going to stretch by a factor of B in the Y direction, and likewise by a factor of C in the Z direction. Does everybody see that? And you stretch out a sphere in various directions, you get what's called an ellipsoid. And much easier to understand from this deformation point of view. Cool. All right. A couple more examples. I'm going to be really quick with these. They're morally equivalent. Here's something to understand. What do I do with this thing? Easy mistake to make, by the way. A lot of students will see this a squared in the denominator and think, oh, I divided by a squared. That's not what we're talking about. You have to be very, very rigidly precise about how you interpret what has happened to the equation. Specifically, I need to know what to replace x with. So notice I really have to rewrite it in this form. And now, let me get rid of all this that's misleading to us. I can see that I have literally done a replacement where everywhere there was an x, that got replaced with x over a. Just a. Right? Because the squared stays there. It's not x squared that's being replaced. It's just x that's being replaced. Is everybody comfortable with that? Real easy to step on that little landmine. Yeah, anyway, nice punchline is that, this is just a, we started with a paraboloid that we already understood. And having started with a paraboloid, the result was that paraboloid got stretched out in the x direction and it got stretched out in the y direction. And so instead of having circular cross sections, it has elliptical cross sections, and thus the term elliptical paraboloid. Everybody good? All right, real easy to mess that up. So heads up, be careful. Likewise, here, our already established hyperboloid of two sheets gets stretched out in various different directions. This is called an elliptical hyperboloid. It's a mouthful of two sheets. Okay. All right, yeah. Mm-hmm.
Can we scroll to the sphere for 1 second?
Mm-hmm. This one here?
Yeah. Mm-hmm. So what's the difference between this formula and the one that we just talked about?
Oh, okay, yeah. So these are all plus signs.
Oh, okay.
Here we've got some minus signs, but that's a plus. And so, yeah, the detailed bevels, yeah, really make a big difference there. Yeah, totally. Is that satisfying?
Mm-hmm. Thank you.
Yeah, no worries. Okay, so cool. Oh, and so here's where I switch now to my next. There are some examples where you have to sort of concatenate two different deformations, and it is easy to sort of get this backwards. I'm just going to first let me sort of outline what would be the wrong process. A lot of students will look at this and think, oh, yeah, well, what am I doing to x? Well, first I'm subtracting 1, and then I'm dividing by 3. I don't know, it just kind of looks like that in the algebra, right? But if you think that through carefully, that's actually not what happens. Let me just point out. If you start with x, if you replace x with x minus 1, and then if you subsequently, keep in mind what we do here, we don't replace algebra. We replace a variable, in this case x. If I replace x with x over 3, that minus 1 is still way over there like that. It is not part of our numerator, and this thing and this thing are not the same. Everybody see that? Yes.
What page is it?
Oh, yeah, this is page 45 of the Math212 lecture notes. Yeah, thank you. So, I mean, again, at a glance, it looks like you're subtracting 1 first and then dividing by 3. But again, you got to be careful. We are doing replacements. It is what it is. Notice it. You just can't approach it that way. Okay. So now, how do I actually deal with this thing then, without sort of messing it up? And we got a couple of options. What I think is the best sequence of options is first to replace, let's see here, I want to be in this mode. First, replace x with x over 3. And then subsequently replace, and by the way, realize, once you've done this, I'm not looking at that anymore. Now I've got a new equation, a new surface. The blue is all that I'm dealing with. And that thing that used to be x is not x anymore. Right? So when I do a new replacement here, this x, only the x, gets replaced with x minus 1. Right? And then notice I get exactly what I wanted to get. This x minus 1 all over 3 is what I've got. So it feels like we're doing it backwards. Right, you kind of have to do the division by 3, if you will, before the subtraction of 1, and it just seems backwards. But again, it is what it is. There it is. You see, you have to do it in this order to generate that expression the way you kind of want to. So be careful about that. It's a nasty little landmine. Now I will point out, yes, to be fair, if you really want to do it the other way, you can rewrite this like that. That's just a little bit of algebra, very easy little algebra. And having written it this way, you can do the subtraction first and then the division by 3, and you get this expression, which, because of the way you pre-prepared it, is in fact equivalent to what you want. But I don't know, I consider this to be okay, well, why would I want to go to trouble for the deliberate purpose of planning to do it in an unnecessarily awkward way? I'd rather just do it what I think is the easier way, which is what I showed first. So anyway. Okay. All right. So let's see here. Let's talk about functions of several variables. Am I on the right page? Yeah, okay, good. Functions of several variables. And we've talked about equations of several variables. Quick little aside. One of the things that you're going to notice starts to become really important in this class, more so, I think, than in previous math classes you've probably taken, is terminology. And you have to use the words correctly, or else you get into trouble. Bad things happen, right? This isn't just me being uptight. This is me having stepped on enough landmines that I don't like stepping on landmines anymore, and I'm hoping to save you all the trouble of stepping on a bad landmine. So, it's very important to understand the difference between an equation and a function, right? So an equation is a statement about different expressions, some or both of which may be functions. But the point is, an equation is a statement, right? A function is not a statement. A function is it's kind of how to think about this. It's like a black box kind of a deal where something goes in, and then as a result of what the function does, different comes out, right? It's an action, you might say, something like that. Right? So very different from an equation. And now high schools, as my experience anyway, high schools are pretty sloppy about allowing students to get away with just completely misrepresenting these words and using them kind of interchangeably. Oh my gosh, you can't do that. That's going to be a catastrophic problem in a class like this. So if you're one of the many students who's been conditioned by your high school perhaps to kind of, not really care much about the distinction between these things, I'm sorry to have to report, but yeah, you're going to have to tighten that up. So be very, very careful about that. A function takes inputs and gives outputs. An equation is a statement about algebraic expressions. They're just totally different things. Okay. All right. Now, with that in mind, so let's talk about a multivariable function. So, again, function is this box. Multivariable just means that there are several input variables instead of just a single input variable. That's the main difference right there. It's just that instead of a single number going in, several numbers go in. Now, of course, notice a list of several numbers is, in fact, also a vector. So this is an alternative way to think of a multivariable function. You can think of it as something where a vector goes in and then stuff comes out. Now, again, that stuff that comes out, you can think of that stuff as being several variables, or you can think of all those several variables as defining a vector that comes out. Take your pick. Okay. Nice to be able to think about it from both points of view. All right, so that's what a multivariable function is. And a little bit of notation here. This thing that went in had in different coordinates. I guess I better leave that up on the page. It had in different coordinates. So thought of as a vector, it is a vector in the Euclidean space Rn. Okay. The thing that comes out, and again, you can think of it as a bunch of different variables, but there were m of those variables. So this thing that comes out is a vector in Rm. And we have terminology, important terminology that you need to know about these spaces, the one where the inputs come from and the one where the outputs go into. The terminology is that the input space, the world where the inputs come from, is called the domain, and the one where the outputs land in is called the target. Domain and target. Now, there's other terminology out there. Sometimes, this thing here that I call the target is in some books called the range. I really don't like that term. And the reason why is that word range gets used to mean something very closely related but importantly different in different textbooks. To me, the word range, because it means different things to different people, has become an almost useless term because it's a Tower of Babel problem. Nobody knows what the other person means when they say it. Right? But thankfully, at least in my experience, the word target is unambiguous. Everybody agrees on what target means. So I strongly prefer the word target. Okay, is everybody on board so far? Okay. Now, another little bit of notation that's important to understand. You can think of a function like this. Again, you notice I've got the function as, I'm drawing it with an arrow representing this action of taking something out of Rn and then putting the result in to Rm. This is kind of a descriptive diagram, you might say, for what the function's doing. A very common notation is this right here. Let me kind of read this off the way it's intended that the reader read this. We've got a function here. Colon says, let me tell you some key information about this function. This says that the domain is Rn. And then the arrow represents how the function takes that over and lands it in the target, which is Rm. So very common notation. I'm going to be using this notation. I encourage you to use this notation. It's a very efficient way to tell your reader what's the name of your function, what is its domain, and what is its target. Very compact, very convenient, and very standard. By the way, I was trying to erase. Here we go. Very standard. Everybody all right? Okay. Alrighty, so here you go. Now we can write down this right here. This is a multivariable function. And notice there are 3 different inputs. I can think of the inputs as being 3 separate variables. Or I could think of those 3 inputs as being the coordinates of a single vector. And it is a vector that comes out of R3. So my domain is going to be R3. The outputs, I have formulas right here for what these outputs are. I can give them names. The first output I'll call V1. The second output I'll call V2. Arbitrarily choosing names. And there are 2 outputs. I can think of them as 2 separate variables, or I can think of them as 2 coordinates of a single vector in R2. Oh, there you go. So, so you can write the function like this, and you can write this equation in the more compact sort of vector form like this. Is everybody comfortable with that? Okay. By the way, a common choice that I do this is just me, but different people. Give me 2 seconds. A common choice that I like is if I have to give a name to a vector whose coordinates are x, y, and z, that's 3 separate letters of the alphabet. I can't use all 3 of them to name the vector that they represent. So fairly arbitrarily, I just like to call it the x vector in a situation like that. It just seems convenient. It's arbitrary, but anyway, that's I do a lot of that. Yes, question?
So in this example, when we went from x to x squared minus yz, for example, were you just supposing that it's... I'm just made up. This is an arbitrary multivariable function I just wrote down so I could kind of... I wrote down an arbitrary function so that I could discuss its domain and its target in various notations. That's all. Yeah. Cool. All right. Okay, so let's talk about some natural examples. Now, I know you all have seen a bazillion single variable functions, and I assume you're highly persuaded that single variable functions are not only important, but ubiquitous, right? They're everywhere. There are just tons of them all over the place, single variable functions. Multivariable functions too. So for example, just the most trite of water cooler conversations is to talk about the weather, right? But if you think about it, the weather is a multivariable function. Because when you're talking about the weather, you're talking about the weather at a particular location, namely at a certain longitude and latitude, right? The weather here is not the same as the weather in Miami, right? You're also talking about the weather at a particular moment. The weather here is absolutely not the same as the weather was 12 hours ago. For one thing, it was dark, right? So weather depends. You got to tell me, before we can even talk about what the weather is, you got to give me some input values. Where are we and when are you talking about? So those are the inputs to what I'm going to call the weather function. The outputs, well, various aspects of the weather that you might be interested in discussing. You might want to talk about the temperature. You might want to talk about the barometric pressure, depending on how old you are. I know older people seem to be much more interested in that. And humidity, depending on where you live. I'm originally from Houston. We talk about humidity a lot, right? So multiple outputs coming from multiple inputs. So as I've got it written here, and this, by the way, is not the only way to talk about the weather. You could talk about all sorts of aspects of the weather. Wind speed, wind direction. There's lots of different sort of additional. So just this streamlined way that I'm describing weather, already a function with 3 inputs and 3 outputs. Everybody good? Okay. Here's one. Suppose you have some small business and you're trying to keep track of how certain things that you have control over will affect certain things that you would like to influence in certain ways, right? And, well, you have control over, how much money you borrow and how many people you hire. And, well, you don't have control over interest rates, but you can at least view that as something that affects your bottom line. And you could reasonably ask, okay, given certain values of my sort of scenario, you might say, I would like to know what results from that in terms of how much risk am I exposing myself to, and how much profit do I stand to generate as a result of the scenario at hand, right? So again, multivariable function. You don't really think about starting a business as involving multivariable functions, but well, it clearly does. Right. So multivariable functions, the point of these examples here is to persuade you that the world is full of multivariable examples, multivariable functions, I should say. And understanding how to do calculus of multivariable functions is correspondingly very important. Okay. All right. Now I'm going to switch over back to the Math219 notes. This is the Chapter 2 notes, page 3, for those of you following along. How do we visualize multivariable functions? I got some bad news here. The answer to this question as pertains to single variable functions is actually pretty simple. Single variable functions, right? High school calculus. Single variable functions, practically every picture you ever saw was a graph. It was a single particular kind of construction that all look the same. They're all generated by well, they don't look the same, but they're generated by the exact same process every single time. So you get kind of accustomed to thinking exclusively in those terms that, okay, well, I know how graphs work, and whenever I see a certain geometric characteristic of my picture, I know that I can infer certain algebraic facts about my function. All of that is a peculiarity of the fact that you're talking about graphs and only graphs. So the problem is, you get too accustomed to graphs in a single variable calculus class, and you kind of very many students will overinterpret from that experience and think, okay, well, every picture that we ever see of any, if it's related to a multivariable function, if it's related to any function, then pictures are all, you interpret them all the exact same way. And it's just not true. We're going to have many different kinds of pictures that are not graphs in this course that we will rely on heavily. So what you're going to have to do in this class, this is, again, there is kind of no single variable version of this, but in this course, every time you see a picture, you're going to have to take an active role in asking yourself, wait a minute, what kind of picture is this? Is this a graph? Is this a level set? Is this a vector field? What am I looking at here? Right? And only once you identify what kind of a picture it is, can you then know what are the appropriate interpretations that I can make from it. So, again, you never had to do that in single variable calculus. It just wasn't an issue. All the pictures are graphs.
practically every one of them. So no such complication here. We have such complications. Okay, so the definition of a graph, here's the kind of the full thing. I'll come back to this momentarily. First, let me remind you of what you already know of basically how you form a graph. If you have a single variable function, right, you got one input, one output, how do you form the graph? Well, y is f of x, and you take the input variable, you make that the first coordinate. You take the output variable, you make that the second coordinate, and then each one of these points, x comma y, you put down a dot in the xy plane. And if you do that for every value of x, compute all the corresponding values of y, generate all these corresponding points x comma y, you get a curve like that, and that is called the graph. Everybody on board? Is that all familiar? Okay, boring. There's something pretty weird about this, though. I don't know if you ever thought about this. They call it single variable calculus. And then they go around drawing two-dimensional pictures. What's going on there? Right? The domain is one-dimensional. The target is one-dimensional. Why do we have a two-dimensional picture? That's a pretty good question. The reason we have a two-dimensional picture is because of the graph construction. The graph that I've drawn, the fact that I have a two-dimensional picture is no way intrinsic to this function. We get a two-dimensional picture because we decided, because we chose that we would like to do this weird thing where we take input variables, where we take input variables and output variables and smash them together to make a single point. That is arbitrary, totally arbitrary, and kind of weird, right? Unnatural. Very useful. But we made that up. That is not part of what the function actually is. So this is one of the first things to make sure you sort of consciously recognize about graphs. It's a very artificial construction, and artificial in such a way that you get, again, a new space in which to look at things that is not the domain, and it is not the target. It's a made-up new space, not intrinsic to the function. Okay, so that's weird. All right, here's another example. Let's see a multivariable version of this. Same sort of thing, same basic idea. We're going to write down an equation, z equals f of x, y. Notice I've got my function f here. F is a function of two variables. And, okay, so I'm going to take my two input variables, x and y. Then I'm going to take my output variable z. I'm going to, again, kind of smash them together in this ultimately pretty unnatural way to take input variables from one space, the domain, output variables from a different space, namely the target, and to smash them together to make a point x comma y comma z. That's a point in 3 dimensions that is not the domain. It is not the target. Right? We made this up. But we get a point there. And now notice that's the point that comes out of, if you will, kind of this point down here in the, if you will, the domain. Right? And if you do that for every point in the domain, then you'll get a bunch of points up here on the graph. And my appeal is that what the function effectively does is it kind of pushes points in the xy plane kind of up by different amounts depending on the value of the function. And so the two-dimensional domain gets kind of lifted to make now a two-dimensional surface. What do you think? Is that cool? All right. Okay. Now here's another way to think about this, by the way. I mean, you can, if we think of this as we start with a function, and a function with a domain and a target, and I've got this thing called f. Another way to think about forming the graph is that I'm making an equation where I effectively just give a name to the output variable. It's really kind of it seems so innocent, but taking the output values of the function, which don't have to have names at all, but once I choose to call those output values by some name, in this case y, notice that act alone of naming the output variables gives me the equation of the graph. So that's this other way of thinking of, how do you form a graph? The way you form a graph is you take your function, you name the output values, make sure to use a new variable that you haven't already used as an input variable. Okay? And the act of naming the outputs creates the equation that gives the graph. Okay. All right, different way to think about it. All right, here's another example. Perfectly innocent scenario. 3 input variables. Well, 3 is more than 2. A little bit more than 2. Seems like this is probably going to be a little bit geometrically more challenging, I guess, or whatever. But notice, if you've got 3 input variables, and you've got 1 output value that you give a name to, we call it W, right? Notice that means that your graph consists of a bunch of points with 4 coordinates. That means it lives inside of a 4-dimensional space, and we cannot even pretend to be able to draw that. So this is a very unhappy little scenario that we've created here. I would like to take this seemingly not that bad function. It only has 3 inputs. It's just one more than the lowest possible multivariable scenario, namely 2 inputs. It's hardly anything to ask what happens if I have 3 input variables, and yet the result is, forget about graphs. You can't draw graphs. Now the question. You can't even visualize it. Everybody? Yeah. Huh?
How many potential solutions could you have for that?
What do you mean solutions?
So, since you mentioned that there'd be 4 points on the graph, does that imply that there's 4 solutions?
No. I'm saying that the graph consists of a bunch of points that have 4 coordinates, and so the graph lives in a 4-dimensional world, right? So in this previous case here, we're talking about the graph points on the graph have 3 coordinates, and that's why the graph lives in a 3-dimensional space. Yeah. No, but of course a function, one of the strict rules about a function can only have, for any given inputs, it has to be unambiguous what the output or outputs are. So functions are only allowed to have which I'm going to call a single output, by which I mean, it could be a variable, or it could be a vector, or it could be whatever other kind of critter, but it can't be, it could be this or that. Does that make sense? Yeah. All right. Yeah. Okay, so this is one of the reasons why graphs are a problem. And in single variable calculus, this is all we're looking at in single variable calculus. That means we always get 2-dimensional pictures. Perfect. We have 2-dimensional paper. The graph itself, the curve itself, right, consists of, as I just said, it's a curve. Perfect. I draw with a 1-dimensional pencil that's tailor-made to make curves. Right? It's just perfect. Graphs are awesome if you're in single variable calculus. In this scenario here, 1 input variable, 1 output variable. This is why they only use graphs in single variable calculus, because they're awesome. Tailor-made construction for that scenario. Doesn't work very well in higher dimensions. So, bummer. Is everybody with me? Okay, so along these lines, here's another one that I think is really important. In a lot of high school classes, you can get away with this kind of nonsense. But a function is an algebraic object. It's a fundamental mathematical object. A graph is a picture that we draw to help us understand a function.
that serve certain purposes. And we like graphs, certainly in single variable calculus. But you got to make sure to understand that these are not the same thing, right? These are different things. Don't blur the line there, because if you see a picture and if you call it a graph, you're making a specific statement about what kind of picture that is. It might not be, right? So just make sure to see the distinction between the function and the graph we use to understand the functions in some cases. And make sure to use the terminology carefully, because again, you can talk yourself into problems. It is so easily, and ultimately this will lead to wrong answers. Okay. All right, moving along. Here's my next example of a completely different construction. This is a picture that I can draw. Graphs are pictures. We like pictures, like to be able to see things. But notice the picture that I'm drawing here does not look like a graph. That's a weird, for one thing, there's I see two different spaces here. There's one on the left, one on the right. That's weird. So very different picture, very different kind of construction, very different way to understand a function geometrically. All this is what I like to call the literal picture. Literal in the sense that I've got a domain here, and I'm going to literally draw the domain. That is what the domain is. It's R3. There's R3. And I've got a target here. That's part of what this function is. That target, okay, R1. All right, there it is. There's R1. What does the function f do? F's job is to take stuff out of the green world and drop it down into the blue world. Kind of like so. Right? So this is really, this picture here is just describing as literally as possible what is happening when the function does stuff. And it's a picture. Right? Now, you could gripe that very validly that this is a pretty bad picture, because I can draw maybe one point A there and say, okay, well, its output value is some other output value f of a over here. But what am I going to do? Sit here and just draw every possible input and its corresponding output? I'm going to run out of colors for one thing. If I don't use colors, I can't tell which one's going to where. This seems pretty bad. And it is pretty bad, frankly. But it's better than this. Right? I mean, this is a total pipe dream right here. Oh yeah, I'm going to visualize a four-dimensional picture. No, you're not. This is worthless as far as we're concerned. Absolutely worthless. This is only mostly worthless, and that's a win. Yeah.
Do we only get to three-dimensioning in this course?
I'm going to give you a complicated answer to that question. I'm certainly not going to ask you to draw anything more than 3 dimensions, right? There are plenty of things that you can do with multivariable calculus that involve more than 3 dimensions. It's just that we're going to only be able to do it algebraically. But yeah, so I make no promises about algebraically what I might ask you to do, roughly speaking, you'll kind of visualize that happening in 3 dimensions or even 2 dimensions. But then, you write down the algebra, you'll be thinking 3-dimensionally, but you'll be writing algebra of 7 dimensions, and that's fine. I mean, the algebra is really not that different. So I will be generalizing in that sense, but it's only going to be algebraically. Does that make sense? Okay. Now, what possible use could I make of this picture? Here's one. I think this is a nice scenario. I've got a input point A. I've got an output point f of A. And one could imagine that, hey, maybe the thing that's at A, maybe it takes off and starts moving with some velocity. Well, look, that input value A was supposed to stay put. If I start moving away from A at some velocity, the output value is not going to stay the same. The output value is going to also move. I don't know if it's going to increase or decrease, but there will be some. That output will start moving also. So this is actually kind of a story, right? I've got my inputs, I've got my outputs. I was at a certain place called A, which had my output at a certain place called F of A, but I took off and started moving with some velocity in the domain, and that results in some output velocity in the target. There's a lot happening in this picture. And very reasonably, I might, for example, want to know, hey, given an input velocity, how would I find the corresponding output velocity? This is actually going to be one of the big questions that we're going to be talking about in this class. This picture at least gives us something to kind of sink our teeth into, something to visualize as representing what is happening when we do this mathematical thing that we're going to, I don't want to say certain keywords here, but we're going to address this mathematically, and this is the picture of what is going to be described when we do start doing that. So we have to draw that picture in this way. Can't even begin to think about this in a graph context. Okay, and I think we're out of time here, so this is a pretty good place to draw the line. Draw the line right there. We'll pick up here on Monday. Y'all have a great weekend, and see you Monday.